Today I will talk about an open source project called Apache Flink and how could we process and transform real-time data using Flink. More specifically, how to build real-time processing Flink jobs using Python and Flink SQL. Now, speed is of the essence in today's business world. Consumers expect real-time services, be it a payment notification or a shopping fulfillment event or a stock trade confirmation. Now, real-time services needs real-time processing of streaming data. A sale, a shipment, a customer experience event needs to be processed and made available to operational teams. Customer satisfaction has a direct bearing on real-time feedback. Now, we have talked about data stream processing, but what is a data stream? Let's break it down. A data stream consists of packets of data or events. At a minimum, it contains a key and a value to uniquely identify the data event. For example, for an Internet of Things IoT sensor, the data stream could have device ID and records of temperature, humidity, etc. Similarly, for a business process change, the customer ID and the change in status would be important data. For a user behavior data, it could be the user session ID and the specific products and sections of the page the user has browsed, etc. So data stream gets perpetually added to a streaming storage system like Apache Kafka. Similar to a database table, the difference being the table in this case has no bounds or an unbounded context. Data gets ingested perpetually till the data producers stop. So to process data that has accumulated in the past, we could create time boundaries between the start of production of data till now and can analyze data streams within a time bounded context. But remember, for future data streams arriving, it is still an unbounded context. Now, such a data streaming platform normally consists of a data source or a producer, a data stream storage like Apache Kafka, a data stream processing or transformation engine like Apache Flink, streaming governance tools, and sinks, which could be operational databases, data warehouses, or other downstream applications. A real world example of such a platform would be these IoT sensors getting data streams aggregated on the edge and then published to a data stream storage like Kafka and processed in real time using Apache Flink and then using a connector. These data streams reach an Elasticsearch index and then the streaming data is visualized using Kibana as a real-time dashboard, which shows the health of these sensors and any anomaly in sensor readings. So, with the concept of a data streaming platform well established, let's understand how Flink fits into this overall picture of a data streaming platform. With heterogeneous sources like Kafka, file system, database change data captures, which keeps on producing streaming data, Flink provides a real-time capability of transforming this streaming data and apply sophisticated aggregations, deduplications, etc., and send the streaming data to a sink. Flink completes a streaming data pipeline by introducing capabilities of transforming streaming data in real time using simple Python domain specific language or DSLs, or writing Flink SQLs within a Python Flink job. While Flink does have lower level APIs to access events directly, like Data Stream API, and even lower the process functions, most of the times developers use Flink's Table API DSLs, specifically Python Table API DSLs, or write Flink SQLs with Pyflink. Pyflink Table API provides an easy option of writing complex stream processing transformations within simple Python scripts. We'll see later how this is done. For Pyflink Table API, a stream of data is abstracted as a Flink dynamic table, and really everything revolves around this Flink dynamic table. All real-time transformation operations are then performed on this Flink dynamic table. For example, in this case, streaming data gets appended for user behavior analysis, and this can be viewed as a Flink dynamic table with the fields user, created time, and URL. This way, it becomes easy to write queries on these Flink dynamic tables. So, As explained in the previous slide, a Flink dynamic table mirrors a stream like a Kafka topic. So a Flink dynamic table always changes with time. A query which is run on a Flink dynamic table becomes a continuous query and processes streaming data as and when it arrives. A continuous query, as you might understand, thus runs perpetually, and the result of the query yields another Flink dynamic table. So with Flink dynamic tables, it becomes easy to write aggregations as well. In this example, with a Flink dynamic table of clickstream data, we could add a group by user, like a normal regular SQL, and the resulting dynamic table will keep on updating the result whenever a new row gets added for a specific user. So for this case, it starts with Marie and the count 1, and the moment Bob adds in the clickstream data, the Flink dynamic table appends that row. And since it's grouped by user and we only want to show the count of URL, the next time when Marie clicks on a new page, the Flink dynamic table updates the Marie record with the count 2. The power of writing such aggregations simply on a stream makes Flink so impactful. Now let's talk a little about a stream table duality. So with a Kafka topic as the stream destination and Flink as the dynamic table mirroring the stream, it becomes easy to create append-only tables from the stream. So in this example, the best sellers Flink dynamic table is populated with rows as and when new data arrives in the orders Flink dynamic table. Continuing on stream table duality, for the update use case, the resulting Flink dynamic table upserts the row for the specific key. So unlike the append use case, where rows would have been appended endlessly, this time bestseller upserts the count for a given key. Just to summarize on this stream table duality again, the upsert capability of Flink creates aggregated dynamic tables, providing a snapshot of the process, of any business process at a given point in time, while the insert capability creates an append-only Flink dynamic table. Moving on, with Flink, it is also possible to write complex window functions on streams to aggregate events over time, using the same Python Table API DSLs and Flink SQL. To go a step deeper, with a Flink Tumbling window, Flink can compute results based on non-overlapping windows with a fixed window size in time. So in this example, the size of the window is 1 hour. Thus, all events that fall within each hour will be aggregated in this function. Now, with a Flink hopping window, the time boundaries may overlap. Remember, for a tumbling window, the time boundaries never overlap, so these are discrete windows. But for a hopping window, the time boundaries may overlap. So in this example, the size of the window is still 1 hour, but a slider moves across the timeline of events every 15 minutes. Thus, we get a result which is aggregated every hour, but the result gets updated every 15 minutes. It's a very, very important use case for calculating rolling and moving average. Now, this is a Flink tumbling window example where we group by results by user every 1 hour. So the tumble interval is 1 hour. Flink provides these sophisticated aggregation functions which could be applied to data streams in flight. So if we focus on the created time, so for every hour, the tumbling window bucket would keep on group by the user, let's say for Marie and for Bob, and would count the number of URLs they have visited. So for this case, the time window is between 12 to 13 hours. For this case, the time window is between 13 to 14 hours. And for this case, the time window is from 14 to 15 hours. So whatever comes in between this 14 to 15 hour window would be aggregated using this tumbling window function. Let's now examine a Pyflink Table API in action. So this is a real Python Flink job, and it starts with a stream execution environment, which is pretty much the entry point for the application for this Flink job. And of course, since it's Kafka with the Flink SQL, we need to add the Flink SQL connector Kafka dependency. And then a sensor reading Flink dynamic table is created. So we have created a Flink dynamic table called sensor underscore readings and associated it with the Kafka topic sensor.readings. Notice the data events are that from an IoT sensor with temperature, humidity, and a ampere hour parameter, which is the battery charge consumed by the device ID. So we want to receive all such sensor data within the Flink dynamic table and use Flink's Tumbling window Table API DSL to process the data. And we want to group by the device ID as well. So now let's look at the Tumbling window Table API DSL in the next slide. So here we have defined the Tumbling window using a friendly Python fluid DSL notation. So this aggregates the calculation of battery charge consumed, which is the ampere hour sensor reading. So we want to tumble over every 30 seconds, which means applying the aggregation of summing the ampere hour or the battery charge consumed value, and then group by device ID, and then insert everything into a new Flink dynamic table, which would be a sync, which could be mirrored as a Kafka topic as well. So in real world, as a next step, we could actually have an actuator as a downstream application for the sensors, which might trigger an alarm if the upper control limit breaches a specific threshold, etc. So here we have done a tumble over 30 seconds on the time for the sensor readings. So we have used the processing time here. We could have also used an event time as well. And then we have grouped by the device ID. And in the new table, we have selected the device ID, name of the device ID, the tumbling window start and end timestamp, and a sum of the charge consumed. So we could have written the same tumbling window Table API DSL using a friendly Flink SQL syntax wrapped around the Python script as well. So the only difference would be instead of the DSL fluid notation, we will do something like a select device ID from sensor readings, etc. But remember, both Pyflink Table API and the Flink SQL statement would produce the same optimized execution plan, which could be checked through a simple .explain function within Pyflink. So we could use either. And I have also uploaded the code in GitHub, so you can scan this QR and get the code. But once this tumbling window is done with its operation, we have created this device charge table, which holds the device ID, the window start, window end timestamps, and the charge consumed, which is a sum and group by each device, which is my sync Flink dynamic table. And I have associated it with a Kafka topic called device.charge. And then I have just run this Flink SQL command by calling the Pyflink execute insert. So in this slide, we see the example of the message. Notice the device ID, the different sensor readings, especially the ampere hour, which is the battery charge consumed, and the timestamp, which is getting passed. And this is being used by the tumbling window operator. For our case, we have used processing time. This is event time. We could have used this as well. So the ampere hour is the parameter where the sum aggregation would have been applied every 30 seconds. So now if you look at the result of the Flink SQL jobs, you could see that 3 device IDs and the sum of the charge consumed for each of these device IDs. And the tumbling window size is 30 seconds. So if you look at the tumbling window start and the end, this one starts at 13:51:00 and it ends at 13:51:30. Similarly, the next tumbling window starts at 13:51:30 and it ends at 13:52:00. And this remains the charge consumed, which is the aggregation which we have done on our tumbling window operator. So with that, we come to the end of my session. Here's my LinkedIn URL and my blog where you can reach me. Hope you liked my session. If you want to get started with Pyflink, I have created a 6-part series on Pyflink on my blog. So please have a read. Bye for now. Take care.